Good afternoon, calculus students. Today we're going to look at the topic of continuity and what that has to do with limits, okay? And so first I just want to talk about what does it mean for a function to be continuous, okay? So basically that means you can trace the graph, with your pencil, you can trace a graph with a pencil and not have to pick it up, right? So there's no breaks in the graph, there's no holes, there's no asymptotes, there's no jumps, okay, in the graph. The graph is nice and smooth. You can trace it with your pencil without having to pick your pencil up. So that's easy enough to say and look at when you have a graph, okay? But how do you prove that without a graph? All right, and that's really what we're going to focus on today. So to prove continuity without a graph, all right, there's actually three things that you have to be able to show, okay? So there are three conditions for continuity at a point. All right, and we're going to call that point C. All right, so it's generic in terms of we're really talking about any possible point on the graph when we say at point C. So the first condition is that f of C must exist. All right, well, remember f of C means the y value is there's a y value on the graph for every x value that you plug in. Okay, so that just means the point at C, the point must have a y value to go with it. It can't be a hole, has to be a closed point. Okay. All right. The second thing is that the limit as x approaches that point, as x approaches C, of f of x must exist. Okay. So the point has to exist and the limit has to exist. But that's not enough because they don't always have to line up. So for a function to be continuous, though, they do have to line up. And to prove that, or to show that they do line up, your f of C must equal the limit as x approaches C of f of x. Okay? So again, condition 1 means the point exists. Condition 2 means the limit exists as we come into that point from both sides. But then condition 3 means that the point exists and the limit exists and they're equal. So that means the point is where, that's where the limit comes into and they kind of meet up. All right, so what are you going to do with this? Well, you're going to have to be able to figure out if f of x is continuous. So is f of x continuous? And I want to know, if not, where isn't it continuous? Okay, you have so technically you're checking every possible point in the domain. Okay? All right, so number 1. All right, so again, we're just being generic. Is it continuous or not? All right, so f of x equals x cubed minus 2x squared minus x plus 2. Okay, well, this is a cubic function. All right, hopefully you know that cubic functions are continuous, as all polynomials are. All right, so cubic looks something like this, right? And all polynomials are continuous. So the question just says, is this continuous? Obviously, yes, it is. And if you want to just make sure that you know why, it's because all polynomials are continuous. Okay? So it doesn't matter. We could pick an infinite amount of C values and check those 3 conditions at every single one of them, and they would all work. Okay? All right. Number 2. G of x equals x squared minus 1 over x minus 1. And all I want to know, I don't want you to do anything else with it, I just want to know if it's continuous or not. And hopefully you remember a little bit about rational functions. If there's a denominator, that means x cannot equal something, right? X cannot equal whatever would make the denominator 0. So if x cannot equal something, then this thing is definitely not continuous. So no, this is not continuous at x equals 1. Okay? All right, well, how about this one? Okay, f of x equals x minus 1 squared minus x minus 12 all over x squared minus 5x plus 4. Okay, well, this one has a denominator also, so it is probably not continuous, all right? But how do you figure out where? You have to factor the bottom. Okay, so in the last one, it was obvious. You just set the bottom equal to 0 and you're good to go. On this one, you really need to factor the bottom so that you can see what x's you would have to basically throw out of the domain. So let's see. We need 2 negatives. 1 multiplies to be 4 and adds to be 5, 4, and 1. So we know that x is not allowed to equal positive 1 and positive 4 because if I plug them back in, they would give me 0 on the bottom. So now we can answer our question, no, this one is not continuous at x equals 1 and 4. Okay? All right. Then I want to look at one other type and ask you the same question. So I'll get one more question here. Question 4. Let's make some more room here. All right, so question 4. All right, this time I'm going to give you a piecewise. All right. And I want to know if it's continuous. All right, and when I say that, I mean anywhere. Is it continuous everywhere? And if you have a piecewise, all right, the only place that you need to be worried that it might not be continuous is where that piecewise changes, okay? So we actually have to check to see if it's continuous at x equals 2. So this is where you actually need to go through and physically, literally check those 3 conditions, okay? And we're checking it at 2. So I want to know, all right, does f of 2 exist? Okay? Am I physically allowed to plug in exactly x equals 2 in one of these pieces? All right? And yes, because of the or equal to right there. Okay? So I am allowed to plug in 2. All right? And so if I did, I would be plugging it into the bottom line. I happen to get 4 minus 4 is 0. All right? So it does exist. I can find it. All right? Now I want to know, and give myself some more room here. Now I want to know, does the limit as x approaches 2 of f of x exist? All right, so that's where the whole limit idea comes in. How do you check a limit for a piecewise? Well, the only way to exist is if the left-hand limit equals the right-hand limit. Okay, so then I'm actually going to have to take the limit as x approaches 2 from the left, and I got to put a specific piece in there, and I want to know, does it equal the limit as x approaches 2 from the right? All right, so then I go back up to my piecewise. All right, x is less than 2 is the left, x is greater than 2 is the right, so make sure you use the appropriate pieces. But once you have your pieces picked out, then remember you just direct substitute. So if I direct substitute 2 in for x on this side, I get 4. 2 in for x on the other side, I get 0. And they are not equal. So this limit does not exist. Well, I don't even have to check the third part of the conditions. If I say no to number 1 or 2, there's no chance number 3 is going to work. So we can go ahead and say So f of x is not continuous, right? That's the answer to the first question, but then where is it not continuous? And that is at x equals 2. Okay? All right, we're going to keep on rolling with some types of discontinuity. Okay? So types of discontinuity. All right. There technically are two types of discontinuity. Essential, okay, and removable. Those are our two main types. But there's actually two different examples when it comes to essential, okay? So I'll try to put them on the same screen here. All right, so keep this in mind. This is separate from removable. All right, so actually let me get myself I'll spread them out a little bit more since I've already divided up my screen. All right, so here, we'll do one there and one here. Okay, so let me draw the picture and then we can talk about them. So let's say that, I don't know, put an asymptote here at 2. Let's go ahead and put one across a horizontal as well. All right, and then let's say my graph looks something like this, and maybe that. Okay, so there's one of them, and let me draw a picture on the other one. Okay, let's say that, I don't know, come in here to an open circle, and then I jump down here. So one side's linear, the other side is quadratic, or some piece, maybe even some sort of polynomial. Okay, all right, so these two are both called essential discontinuity. All right, this first one is not continuous. At x equals 2 because of the asymptote, because of the vertical asymptote. And we call that, if it has a vertical asymptote, that's called infinite discontinuity. Okay, hopefully you can read that. Infinite discontinuity, because the graph goes off to infinity in one direction or the other, but again, like when you're talking about continuous, there's no way to trace this graph, right, both pieces of it, and not pick up your pencil to move to the other side of the asymptote, okay? All right, the second type here, that is called jump discontinuity. Kind of obvious the reason it's called jump, because literally the graph, it's almost like it stops at, stops at one y value and jumps to another y value. Whether they line up or not, that doesn't even matter either. So if I were to talk about this one specifically, this one would be not continuous at, well then you have to figure out what's the x value where it jumps, and I put it on the axis so it was easy to say it was not continuous at x equals 0. All right, and those, they are grouped together as essential discontinuity because there's really nothing you can do to fix it, all right? Meaning you can't change the function in any way and still be a rational function or still be a piecewise, and like, you can't actually change the function to make them continuous, all right? You'll see what I mean in just a second. All right, so let's look at removable. All right, here's an example of a graph of something that's removable. All right, let's say I draw this. All right, so it's almost continuous, but it has a hole in it. Okay, and let's pretend that that hole is at, I don't know, 2, 2. Okay, I'm just pretending. All right, well, you can tell me that it is not continuous, right? So if I asked you if it was continuous or not, you would tell me that it's not continuous at x equals 2. Okay? So if that's all I was asking, you'd be done. But then I want to know if it's removable or not. And it's removable because the discontinuity is just a hole. All right, but there's like a definition for that, okay? So if f of x, sorry, let me go back. No, let's just do not f of x. If f of c does not exist, so that means there's like the point itself does not exist, but the limit as x approaches c on that function does exist, right? The discontinuity is removable. And what that means is we can actually rewrite the function just slightly different, right? So I'm not really changing the function altogether. I'm basically just going to add an extra little piece in there. I just want all these boxes to go away. Sorry, I'm just clicking. Okay, so we're just going to add an extra little piece to our function that's going to kind of fix the hole or plug the hole, and then it will be a continuous function. Okay, so let's extend our practice problems. All right, so I'm gonna so I still want to know, well, I still want to know, is f of x continuous? Okay, if not, where? All right, and is that discontinuity, if it's not continuous, is that discontinuity removable or not? If so, fix it. All right, so we've got a lot of stuff going on here. All right, so we have to figure out if our function is continuous. If it's not continuous, where is it not continuous? And then, is that discontinuity something we can fix? Meaning, is it removable? Is it just a hole? All right, or is it an asymptote, or is it a jump? Okay, and if it is removable, then I want us to actually look at how to fix it. Okay, so this is example number 5. Hopefully I'm on the right one. All right, and it's actually one that we've looked at before. Okay, so we've already said that this thing is not continuous at x equals 1, right, because of the denominator. But I want to know if that's an asymptote or a hole, because if it's an asymptote, it's not removable. If it's a hole, it is removable. Okay, so then how do you figure that out? Well, that goes back to seeing if you can simplify the function at all. And so I'm factoring the top and the bottom, and I'm going to see if they have any factors that cross out. If the factor on the bottom, if the thing that gave me the discontinuity, if it crosses out, right, that means there is a hole at that x value. Okay, now I specifically want to know where the hole is, not just the x value. I want to know the actual open point if I were to graph it. Okay, so in order to get that, right, you have to know where your hole would be for the x value, that's x equals 1, but then you plug it into the reduced function, and that will tell you that the y value of that hole would be 2. So we have a hole at 1, 2, and since it is just a hole, okay, so it's not continuous at x equals 1, but it is removable. All right, so I'm just like going through and answering the questions. Is it continuous? No. Where? At x equals 1. Is it removable or not? Removable, okay? The reason I wrote down the hole is because that's going to help us fix it, all right? And what I mean by that is we're basically going to rewrite the function, the original function as a piecewise, okay? Now, the original function is fine, right? As long as x is not 1. That function is fine, right? It's continuous everywhere else. So I want to stay that function everywhere else. But what I want to do is I want to make sure, okay, that when I create my second piece, when x does equal 1, I want to make sure I get the y value that would line up with the rest of the graph, okay? Well, that's where the hole is. So I want to use literally the y value where I know the hole is, okay? So what does that do? Okay, so let's just take a look at our piecewise function and see if it meets the 3 conditions of continuity, okay? And so now I want to know, does f of 1 exist? All right, well, it didn't in the original, right? It was not allowed in the original, but is it allowed in the new one? Yes, because I'm allowed to equal 1 in the second piece of the piecewise function. All right, f of 1 equals 2. It does exist. All right, does the limit as x approaches 1 of f of x exist? Okay, well, how would I take the limit of a piecewise? I need the left and the right. But when we're not equal to 1, that is the left and the right. Okay? X not equal to 1 is the left and the right. So the limit would have to exist because we'd use the same function to find it. So let's just make sure we can find it. All right? So if I want the limit as x approaches 1, all right, I have to use the top piece of the piecewise. Direct substitution gives me 0 over 0, but we also know that this thing reduces to x plus 1. And when I take the limit with direct substitution now, the limit is 2. The limit definitely exists. And last but not least, all right, does f of 1 equal the limit as x approaches 1 of f of x? All right? And because of the way that we defined it, okay, so we defined f of 1 to equal 2, and the limit equals 2. All right, so that is true. So now all 3 conditions are met, and we have, by the way, this is a mathematical symbol for therefore. It's like a triangle of 3 dots. Therefore, f of x is continuous. All right, and that means continuous everywhere. Okay? All right, I got a couple more for us. I know we're kind of running long, but I want to give you some more examples. All right. Number 6. All right, it's a function that we've seen before. So we're going to be able to run through the first stuff pretty quickly. All right, is this thing continuous? All right, and we already saw back in number 3 that it was not continuous at x equals 1 and 4, and that was because the denominator factored into x minus 1 and x minus 4. All right, so then I want to know if either one of them or both of them are removable. Okay, and so then I actually need to factor the numerator. All right, you can pause it and factor it if you want to for practice. All right, and I want to see if anything crosses out. All right, well, since both of them cross out, okay, both are removable. Removable. All right, now, if one was removable and one was not, meaning one factor crossed out and the other one didn't, there's nothing you can do to fix that function, okay? But if both are removable, you can fix the function, okay? Because if the factors cross out, remember that means you have holes. right? And I want to know where are those holes, okay? So I know the x values, 1 and 4, but how do I get the y values? Well, I'm just going to use my reduced function and plug in my x values. 1 plus 3 is 4. 4 plus 3 is 7. So I know exactly where my holes are, okay? So now if I redefine, that's what we're really doing, redefine f of x, okay? That's what I mean by fix it. All right, we're going to redefine f of x as a piecewise, okay? It's going to be the original f of x function, because that still has to be there. You can't change that, okay? And it is still going to be that function anytime x is not 1 and 4, okay? But what if x is 1 or x is 4, okay? Well, I need to make sure that I define this function to plug the holes, okay? So that means I want to use the y values of my holes. When x equals 1, I want my point to be at 4, because that's where the hole was. And when x equals 4, I want my point to be at 7, because originally that's where the hole was. And so now if you go through all the 3 conditions to check continuity, be careful here, because if a piecewise has something happens at 2 different places, you would have to check, all right, the 3 conditions for continuity at both places. All right, so you'd have to go through those 3 conditions twice to prove it, okay? And of course, you know, you should always do that for practice. All right, the last 2 should go a little bit quicker. All right, so let me give you a piecewise, whoops. All right, so if I give you a piecewise, like I did earlier, same one I gave you earlier, all right, and I want to know if this is continuous or not. Remember, we said it was not earlier, right? We said it was not continuous at x equals 2. And remember, we had to check 2 because that's where the inequality changes, okay? Now, I want to know if it's removable or not. Well, removable means that place is a hole. But if you go back to when we did this problem in number 4, the reason it was not continuous was because left-hand limit was not equal to the right-hand limit. When we checked the limit as x approached 2 from the left and the right, all right, so because the left-hand limit was not equal to the right-hand limit, and you can go back and look at your work from before, okay? All right, this discontinuity is not removable. All right. And then last, but certainly not least, whoops, I just want to extend the page here. Number 8. All right, here's another rational function, squared x minus 12. All right, so these 2 polynomials, these 2 quadratic functions, the one on the top and the one on the bottom, we've actually seen before, but I wanted to put them together and leave a little bit out for a reason. So remember, if we're doing continuous, all right, we know it's not continuous wherever the bottom equals 0. So you are going to have to factor that bottom again. Okay, and so we know that this thing is not continuous at x equals 1 and 4. But then I want to know if those are removable or not, okay? So that's when you have to factor the numerator, all right, which we've done earlier, okay? And if a factor crosses out, okay, that means there's a hole, all right? So x equals 4 is removable, all right, because there's a hole at x equals 4. But x minus 1 did not cross out this time, So you need to say something to of the effect like x equals 1 is not removable. Okay? And if even one part of it is not removable, there's no way to fix it, to redefine it and fix it. So the practice that I want you to do that goes with this is on page 79. I think it goes on to 80 a little bit. All right, you're going to look at 35 through 58. And that sounds like a lot, but all you're doing is telling me if it's continuous or not. And if it's not continuous, where is it not continuous? Okay? And then is that continuity or that discontinuity removable or not? I'm not asking you to fix any of them. Okay? So that shouldn't really take you too long. All right, and that's all I have for this first video on continuity. I do have a little bit more, but we're going to do it together in class. So I'll see you in class.